Hello, this is the second part of chapter 2.8, and we will continue talking about subspaces and explore the idea of null subspaces and basis for subspaces. And again, this is the extra material we just explore you in the preparation for the future chapters, and this material would not be included on the test one. Okay, and last time we'll start talking about the ideas of subspace, and that it's really kind of simple set which has three properties, and we try to explore how to find a subspace which will goes along with a given matrix A. And we find that the solution of the matrix can be really useful, and particularly if we have a vector which belongs to the column space, it will become a solution of the matrix equations. But we didn't know if it's a subspace or not. So today we will just look at the very specific set of our matrix equation, the homogeneous equation AX is equal 0. And this equation is called a null space, and it's actually form a subspace with all the three properties of the subspace. So basically, null space is always will be a subspace, and in other words, so the system of the solution given but from the system of homogeneous equations will always form a subspace. And why do we care about that? It's because the null spaces can be extremely useful because they can form the basis, the set of vectors which can be expressed as a linear combination. And I know that this chapter and these definitions probably sounds very confusing, but just go along, try simple techniques, and we will exploring the most of the ideas in later chapters. It's just the preparation for you. But you probably all already familiar with the basis of subspaces. I know the definition sounds mysterious, but if you ever done any physics, you probably work with a set of 3 unit orthogonal vectors, E1, E2, and 3. And you already know that every point in a 3-dimensional space can be basically written down as a linear combination of these 3 vectors. So they are the basis of 3-dimensional space. And you can just, test the basic definition of subspace and prove that these 3 vectors in 3-dimensional space form the basis. But for purpose of this chapter, all you need to be able to do is basically find the basis for the subspace given by the given matrix. So, and I know it sounds complicated, but it's actually not that bad. All you need to do is solve the homogeneous equation formed by the matrix, which all of you should be able to do at this point, and find the parametric solution, which give us a basis for the null space. But let's just don't rush and go slowly from the solution. Okay, so we are looking for the null space, and null space are given by solution of homogeneous equation. So we will just need to write down our augmented matrix for our homogeneous equation, which is just our matrix A with a column of zeros added at the end. And if we find the solution, we can write it down as a linear combination of as many vectors as many free variables we will get. But okay, let's just reduce our matrix to the echelon form because that's the easiest way to find the solution. And this is a really good case because look, we have 1, 2, 3 free variables. So the columns 2, 4, and 5 missing pivot position, which means that they are free variables. So we can write down our solutions in terms of free variables, which is x1 in terms of 3 variables and x3 in terms of 3 variables. Okay, we almost done here, all we need, but our question is not just to find the solution. We need to find the basis for null space, which means that we will write down arbitrary vector x as a linear combination of several vectors. Okay, so we are dealing with like we have 5 columns, so we will have a 5th dimensional space. So we will have entries for our variable x1, x2, x3, x4, x5. Okay, let's express our vector in terms of our free variables, x2, x4, and x5. So it's kind of look rather long, but you know, maybe we can write it down as a separate vector for each free variables. For example, we'll factor out the x2 and x2 multiplied by 2 in the first row. So we will write parameter 2. X2 has a factor 1 in the second column. We'll write 1. And the other 3 rows do not have x2 at all, so we have zeros. Okay, so we will call this new vector, just give it a name u. Again, it's just the notation, just to make it easier to write things down. Okay, let's go for the next 3 variable, x4. Again, we have factor 1 from the first row, no x4 in the second row, so we'll put 0. Minus 2 from the third one, 1 from the fourth, and 0 from the fifth. Okay, so we have now x4 times the 5th dimensional vector, and we'll call this vector v. Finally, we will repeat the process for variable x5, and again we have x5 multiplied by the vector, and we call this vector w. So look what we have now. Now we have our arbitrary solution written as a linear combination of the weights, our free variables, x2, x4, and x5, and 3 vectors, u, v, and w. And those 3 vectors actually, again, we'll write it in the linear combination form just to have a short annotations. And these 3 vectors, u, v, and a w, will form a basis for the null space of our matrix. And okay, don't worry if you cannot go properly through the whole process. We will explore these ideas more in the future chapter. But right now, go to the end of the chapter 2.8 and solve couple test exercises to feel a little bit more comfortable.